In the previous lecture, we saw we derived the equation of state for an incompressible and a compressible fluid, compressible medium like air. For an incompressible fluid, the density does not change regardless of changes in pressure, so density is constant. But in seawater, we know that the density is a function of temperature and salinity, and we wrote down a linear relationship between the changes in density and the changes in temperature and salinity. So we started out with trying to close the total governing equations that we have, but we introduced new terms. We introduced new variables, that is temperature, salinity, and specific humidity, while deriving the equation of state. And then we tried to derive an equation governing the temperature, the variable temperature, and we saw that we derived the energy equation, which gives us the evolution of temperature. So now we will write down similar forms for the evolution of salinity and specific humidity. So governing equations for salinity and moisture. When we are calling it moisture, this is we had seen that we have introduced this variable Q earlier, which is specific humidity. We are calling it moisture. This is the amount of water vapor that is there in the whole parcel of fluid that you are interested in. And salinity is is something that is inferred from conductivity. It gives you the amount of salt dissolved in the seawater. So we have so we need some governing equations. We are not going to do a detailed derivation, but this both of these for seawater, I mean, we can write the salinity in terms of a diffusion equation. So we'll just write down the forms of the equations. So for seawater, we can write down a diffusion equation for the evolution of salinity. So capital dT is again the total derivative of the material derivative, and this is in terms of this is the Laplacian of the salinity. I mean, this is the total derivative of salinity is proportional to the Laplacian of the salinity. So if you have not yet seen this this operator, this is the operator which is del squared del x squared plus del squared del y squared del z squared. So this is the Laplacian operator. This is the sum of the second partial derivatives. So this, if you look at this carefully, this equation carefully, this looks like the Fourier law of conduction for temperature that we saw earlier. So similarly, we have wrote down similar equation for the evolution of salinity here. So here this is kappa variable. So this is the diffusion coefficient for salt. So this is kappa s. So this is diffusion So this is the diffusion coefficient for salt. S is the salinity, the del square is the Laplacian operator. And this diffusion coefficient, just to give you understanding of what this diffusion coefficient means, this gives you an estimate of the amount of diffusion of that quantity, so of that variable. So in this case, this is salinity. For example, if you add salt into a bucket of water, the amount of time it would need to be fully dissolved in the bucket of water just by molecular motion gives you an estimate of the diffusion. So if diffusion coefficient is high, the salt will variable, I mean that quantity that you have added in water will diffuse faster. If the diffusion coefficient is low, then it will diffuse slowly. So just to give you an order of estimate, temperature diffuses much faster than salinity in seawater. We'll also get to this point later, and why this gives rise to some interesting differences. So this diffusion coefficient also, again to mention, acts something analogous to how viscosity acts for velocity gradients. So here you can see we have Ks times the Laplacian of the concentration, that is the salinity here. Similarly, we had in the momentum equation, if you recall, we had viscosity times the Laplacian of the velocity. So here, I mean, this case del square S is similar to how velocity gradients are killed by viscosity. This is how the diffusion mechanisms are killing the gradients in salinity in the fluid which has salt dissolved in it. So here this is all molecular diffusion. So this is all molecular values. I mean, this is molecular motion that we are considering at this point. But we'll also get to see how turbulence increases this diffusion coefficient actually by multiple magnitudes. So we are yet to go into turbulence. That is the reason I have not introduced those terms, but we'll get to it soon. I mean, towards the latter half of the course. So for moisture also, so we can write similar diffusion equation, even though. So for moisture also we write similar diffusion equation. So here again this is kappa, this is not K. So this is how we can also write down the diffusion equation for moisture, but this has slight complication. I mean, it's not very straightforward in the sense that the specific humidity evolution is a bit more complicated, because unlike that in seawater, there is release of heat, the latent heat of condensation during in a moisture laden air. So if there is something the water vapor has condensed into droplets, it releases the latent heat, and that gives rise to slightly complicated dynamics. But just for simplicity, just for the sake of simplicity, we assume that the evolution of the moisture can be represented as a diffusion equation, similar to how temperature and salinity diffuses in a medium. So this is the diffusion coefficient. So this is the diffusion coefficient for moisture or the specific humidity. So Q, we had define Q to be the specific humidity. We are calling it moisture here. This is just a short form, or more of a colloquial name for specific humidity. So now we are towards the end of the whole derivation of the set of governing equations that describe the fluid motion of seawater or atmospheric air. So we have derived the mass conservation equation is also called the continuity equation. So we have derived the conservation of mass. We have derived three momentum equations. Because there are, I mean, we are using a Cartesian coordinate system with three orthogonal directions, and we have three momentum equations in three directions. So we have three momentum equations, and we have seen that the momentum equations are they are changed when we are measuring from a rotating frame preference. So this is where we introduce the fictitious force, the Coriolis term, and we also had a centrifugal term. But centrifugal term is can also be clubbed into the gravitational acceleration, because that's a conservative force. So we saw that the momentum equations change with the introduction of the rotating frame of reference. So we saw how how all the three equations change. So we have the mass conservation equation, we have three momentum equations. So we have an equation of state. So we have an equation of state. So we saw that for an incompressible fluid, equation of state is just rho equal to constant, whereas for a multi-component system like seawater, where there is temperature and salinity, the density is assumed to be a linear function of temperature and salinity. And because we introduced temperature and salinity as new variables, we need additional equations, which are equations of which is the equation of energy, or the energy equation. And then we have equations for seawater, for salinity and seawater salinity and moisture. So we have the salinity equation, the equation of moisture. So how many equations do we have? So we have one equation here, we have three equations here, we have one equation here, we have one equation here, and we have one equation each here. So here 3 plus 1, 4, 5, 6, 7 equations that describe the evolution of seawater or atmospheric air. Remember that we have also done some kind of simplified assumptions. For example, in the moisture, we have said that we are neglecting the effect of latent heat of the latent heat release when water vapor condenses. So we have not taken those complicated things into account at this point, but this is sufficient for our purposes. So we have derived all these set of equations, and this completes our set of governing equations. Of course, governing equations, these are partial, many of these are partial differential equations where without boundary conditions we cannot solve these equations. We'll need those boundary conditions. We'll come to those. At this point, we'll just stop at the governing equations. We'll do some related topics on how changes in density can be neglected in certain portions of the momentum equations, because we will be dealing with changes in density, varying systems. Because in seawater, density changes, because if you go from one height to another, you will face different densities. So we'll see how those changes affect the momentum equation and which are the terms that we can neglect based on some assumptions. So we'll get to the boundary conditions later, but we will see how some approximations can be used and how those approximations simplify the governing equations. So first approximation that we start with is called the Boussinesq approximation. So this Boussinesq approximation is named after French mathematician and physicist Joseph V. Boussinesq, and who is known for pioneering work in hydrodynamics and elasticity and other areas of physics. So this is an additional simplification where we say that the variation of density in the fluid is can be ignored unless it's multiplied with the gravitational acceleration term. So we'll see what that means. So this can be applied to systems where density does not significantly vary. It does not vary significantly. Okay, so this is true for most of the scenario that will be most of the cases that we'll be dealing with. So most of the phenomena in the ocean or atmosphere happen, for the ocean it happens in a state where density is not significantly changing, and because its dependence on temperature and salinity via the coefficients of thermal expansion and haline contraction is not very strong. So the density changes as you go down in depth is not significant. Similarly, the atmospheric phenomena that we are interested in happen near surface, or at least in places which are lower than the height of the total atmosphere. So most of the weather phenomena, of course, happened in the troposphere, but we are in this approximation, we are assuming that the phenomena are happening near about the surface. So it's less than a kilometer scale phenomena that are happening, which we are interested in. So this is, you know, what is tropopause by now. We have also introduced this term earlier. So we are assuming that the systems, the flow or the winds that we are interested in are happening at a lower level. So we are not going for very large scale motions at this point. So we are confined to small scale motions where density is not varying significantly. So if you go from one level to another, the density is not varying. So density does not vary significantly. The scales of motions are not very high. The scales of motion are not very large. So these are some of the restrictions that we place on our motion to apply the Boussinesq approximation, and why the Boussinesq approximation is needed to simplify the equations of motion. So the Boussinesq approximation states that the density changes in a fluid can be neglected except when it is multiplied by the acceleration due to gravity g. So this is also valid for low flow speeds. So how low? So Mach number is less than 0.3 in very small flow speeds where not appreciable pressure differences are generated. We can assume the Boussinesq approximation to be valid. So now to see how that modifies our governing equation, we told that this will simplify our equations, and that is the reason why we do this. And this is an approximation that holds well, as I have already clarified the points with you. This holds well in the phenomena that are happening in the ocean, because density changes are not very large, and the near surface atmospheric phenomena. So let density rho vary as rho naught plus rho prime. So rho prime is a function of x, y, z, and t. So rho prime is the fluctuation as the notation goes, and rho naught is a reference value. So rho naught is a reference value. Now here the restriction that we have is that rho prime, the magnitude of rho prime is much less than rho naught. So let's say we want to draw some kind of a profile. If this is density, this is rho naught, which can have some variation with some coordinate, let's say z, and we have rho prime on top of this. So rho prime is much smaller, whereas rho naught is rho prime is much smaller than rho naught. So density variations are the total density is of course rho naught plus rho, but rho naught plus rho prime, and rho prime being much smaller than rho naught. So density can of course vary here with respect to change in temperature and salinity, but the only restriction is that the variation is small. So now the continuity equation. So we'll write down the continuity equation that we had derived earlier. Del rho by del t plus del dot rho u So we are not making an assumption of incompressibility here. We are writing down the full continuity equation for any fluid, either it's a compressible or an incompressible medium. So now substituting, so substitute equation 1. So substitute equation 1 in the continuity equation. So we can write del T rho naught plus rho prime plus del dot del dot rho naught plus rho prime cube. I just substituted rho equal to rho naught plus rho prime from equation 1. Now this one can be expressed as del rho prime by del T plus del dot rho naught u plus del dot rho prime u equal to 0. Now there are two terms which have rho prime here. This has rho prime, this has rho prime. So now the first term, let's say this is term 1, this is term 2. Term 1 scales as, so this is del rho prime by del T scales as rho prime by T, which is equal to rho prime L by U equal to rho prime U by L, where U and L are some representative velocity scales and length scales of the problem. And this will be defined by the system that you are interested in. If you're interested in a large scale system, L will be large. If you're interested in a high speed system, U will be large. So rho prime U by L. So this is how the first term scales. So this is, I mean, I'm doing an order of magnitude analysis. So I'm just to make sure this is the first time we are probably doing this. So this is the order of magnitude analysis. So d rho prime by dt scales as this one. And term 2, so this is term 1, the term 2 also scales as rho prime u by L, because your divergence operator is 1 over, has a dimension 1 over length, and hence term 2 also scales as rho prime u by L. So these are the order magnitudes of term 1 and term 2. Now term this the reason why I'm naming this term 3 is because this is I mean, I could have also named it term 2, but I wanted to take the first and the last term first, hence I named it hence I'm naming it sequentially. So term 3 scales as rho naught u by L. Now you can see that in all the cases everything scales as rho u by L. I mean, u by L is constant, whereas term 1 and 2 have rho prime, and because rho prime is much smaller than rho naught, this is where we have put the restriction. So rho prime u by L is also much smaller than rho naught u by L. So we get that terms 1 and 2 are much small than term 3. So this is the by order of magnitude analysis, we find that the term 3 is much larger than the other two terms, and hence the dominant balance in the equation. So the dominant balance in the equation is del dot rho naught u equal to 0. So this is the dominant balance. Not that this, I mean, this is a term which is derivative of the velocities in in different directions. So the dominant balance says that only this derivative, this divergence term is equal to 0, whereas the other terms are negligible here. So this is the same form as the incompressibility equation. So we get to the same form. Remember, there is a difference. So del dot rho naught u equal to 0, as rho naught is constant, we get del dot u equal to 0. So this is the final form that you are writing, as rho naught is constant. So this is the same form as the incompressibility condition, but we derived it from the full continuity equation using the Boussinesq approximation only. So this gives us the same form if the density rho naught is constant. If the density rho naught is a constant, then we get the same form as the incompressibility condition. That is within the Boussinesq approximation also, the velocity field should be divergence free. Now we'll look at the momentum equations. So the momentum equations, so they are also simplified. So we have already derived the momentum equation. So we'll write down the momentum equation again, just for the sake of completion and also to remind ourselves. So we have the momentum equation. So I will not write down the Coriolis acceleration term just for the sake of simplification. It does not matter in this case because the Coriolis term does not have a density multiplied with it. So and we will anyways I mean, we can extend this to this equation to include the Coriolis term and do it, but just for the sake of simplification at this point we are just stopping. I mean, we are assuming that we're using we're measuring from an inertial frame of reference and the Coriolis term is not needed. So consider a background. So consider a background reference state of density rho naught and the pressure is P naught. So P naught so this is the P naught. So the gradient of P naught is equal to rho naught G. So P naught is the reference pressure. This is a function of Z, and this is equal to the rho naught C. This is a background reference state. Now subtract this background reference state from the momentum equation. Actually it's momentum equations, so these are three set of equations. So the momentum equation, subtract it from the momentum equations and use the fact that P equal to P naught plus P prime and rho equal to rho naught plus rho prime. So we have density and pressure which are varying from a reference state. So using that, so rho del u del t equal to minus grad P prime plus rho prime G, sorry, mu del square u. So here we have subtracted the base state and hence we are left with only the fluctuations P prime and rho prime here. So dividing by rho naught, so dividing by rho naught, we have, remember rho equal to rho naught plus rho prime. So we have 1 plus rho prime by rho naught del u by del t equal to minus 1 by rho naught gradient of p prime plus rho prime by rho naught g plus nu del square u, where if you recall, nu is the kinematic viscosity defined as the dynamic viscosity by a reference density. Should write it clearly. So nu is mu over rho naught. So if we had a Coriolis term, you can just divide the Coriolis term with the reference density rho naught. This will not change the use of this approximation here. So I mean, we'll see that we'll only keep the rho prime whenever it appears with gravity. So the Boussinesq approximation. So here, as you can see, we have variations with multiple terms. So we have, I mean, primarily here in this acceleration term, we have this variation of density multiplied with du dt. Now this makes calculations, numerical simulations complicated. So what we do is we apply the Boussinesq approximation. So we invoke the Boussinesq approximation. So neglect all the terms. So where I mean, neglect the density variation where it is multiplied with terms other than the acceleration due to gravity. So we from this previous equation we only get, so del u by del t is equal to minus 1 by rho naught gradient of p prime minus rho prime by rho naught g plus nu del squared u. So we have neglected all multiplication of term of this rho prime term anywhere except when it is multiplied with gravity. So we have kept this term. This is the essence of the Boussinesq approximation. This is important. This is very important for us to keep this.